Continuing what may be one of our more intense modules for this semester, we're going to talk about magnetic fields of current loops and solenoids, which is where we left off in our second lecture. And this is exactly where we left off. We defined that the magnetic field of a loop of current would be B equals mu 0 I over 2R. Now, when we're talking about loops, one of the things you can do is have more than one loop. So this is the magnetic field of a single loop. But of course we could put a second loop next to it, or a third loop, or a fourth loop. And this is usually written as N. So the magnetic field due to a group of loops will be B is equal to N mu 0 I over 2R, where N is the number of loops that you have. And here we have a diagram comparing a loop of current here due to just simply the loop, and here comparing it to a bar magnet. So as you can see, here is our loop. Our current, by our right hand rule, will spiral this way. So our current is going this way, giving our magnetic field this direction. Now at the bottom of the loop, the magnetic field will go in the opposite direction. That's why we end up with this sort of weird looking figure 8 magnetic field. These two are not joined. These are magnetic fields set up by one side of the loop and the other, both going in at the bottom, but both going opposite directions outside of the loop. And this is exactly the same as the thing we would see from a bar magnet. Now, we can also put, say, multiple loops together. So if we take a wire and then we coil it up, what we really are creating here is a solenoid or an electromagnet. That means we can take all these loops. So here this would be dictated by our previous equation, N mu 0 I over 2R would be this magnetic field B. We would end up with our magnetic field spiraling this way and this way, and in the center being in a straight line. So this is essentially a bar magnet that we can use the inside of the magnetic field. So this is a straight line in here. So it's a bar magnet we can put things into. And of course we can reverse these magnetic fields either side by switching the positive and negative terminals of our battery. It's also a magnet, essentially like a bar magnet, that we can switch on and off. Typical examples of this would be the kind of thing you see at car crushing plants, where a magnet can be used to pick up a car and drop it, and it can be switched on and off. Or automatic door locks, things like that. So a solenoid is defined as a wire that's tightly wound into a helix and has lots of closely spaced turns, numbered N. And they're really a set of circular current loops side by side, and they produce a strong uniform magnetic field inside the loops. So outside the loops, as we've seen, it's pretty non-uniform, but it's a nice straight line inside the loop. It's like being inside a bar magnet. And there's your typical solenoid. Current comes in here, twists around, and then exits here. And as I said before, here's our sort of example of a bar magnet versus our loop of current. So this is a loop, a solenoid from the side, and there's the way our magnetic field would be inside of it. You can actually see this using experiments. So here's a solenoid going into a magnetic fluid. So this is a fluid with lots of little metal particles in it. And if you switch on the current, you can see you have a nice straight line inside, influenced a little bit by the fluid here, and then you have your magnetic field curling around on the outside. So if we want to find the magnetic field of our loops of current of our solenoid, the magnetic field of a solenoid is this. B will equal mu 0 n over L times I. So we're factoring out that mu 0. N here is going to be the number of loops that you have. L here is the length. I is the current. Now, there's something I have to point out here, and that's the difference between big N and little n. This big N, if you're dealing with big N, you would need the length of your solenoid and have to calculate N over L times I. If you're presented with little n, this is already the number of turns per unit length. So number of turns per unit length is little n. If you have big N, you'd have to divide it by L. Don't take little n and divide it by L, because then you'll end up in trouble. So here L is 3, and here we have a height of 2. This L value here would be n over 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 divided by 3 would already be this. So be careful. Don't divide little n by L, but big N over L. And there's just a graph of the magnetic field of the solenoid. As you can see, it's quite constant inside and falling off either side of the solenoid. And there's the graph versus the actual distance through the solenoid itself. So these things can be kind of useful. If we take a solenoid and we pass a current through it, it behaves like a magnet that we can switch off, as I said. That means we can switch on this system, and if we put a piece of iron inside it, that piece of iron will feel a magnetic force and be retracted. There is a bit of a payoff here that we're not getting energy and movement energy for nothing. The kinetic energy doesn't come free. It actually winds up heating up this movable iron core quite significantly, as I had a physics professor who enjoyed burning his students. And this is really useful in a lot of places. Electronic door locks. Anybody who can open their doors using their smartphone. Anytime you use some kind of ignition system on a car, you're using a solenoid. Here's a solenoid on a boat, which once failed and left my engine stuck in the down position. Things like microphones and the speaker in any type of speaker, or especially the pickups of things like electric guitars. All of these can use a solenoid system. Let's take a look at a problem. We've got a long solenoid with 1,000 turns uniformly distributed over a length of 0.4 meters, and we're producing a magnetic field of 1 times 10 to the negative 4 Tesla in the center. What I is needed, what current is required in the windings for that to occur. So we've got the number of turns, we've got a length, and we've got a magnetic field. We want to find the current. So be aware of what type of N we have here. We have 1,000 turns and we're given a length of 0.4 meters. So we have to use little n is n over L and calculate that. N is 10 to the 3, 1,000, L is 0.4, B is 1 times 10 to the minus 4. Let's solve for I. So here B is equal to mu 0 Ni. This is mu 0 Ni essentially over L. So I will become BL over mu N. Substitute in. You could, of course, calculate little n separately if you so desired, and then substitute that in. I chose to do it all at once. Substitute the values in, and we'll get an answer of about 3.1 times 10 to the minus 2 amps, or 31.8 milliamps. And as you can see, the Tesla here, relatively small, which is what we would expect. Now, we've already discussed what happens when we have a charged particle moving through a magnetic field. But in some cases, you might see what's referred to as crossed fields. This is where you have an electric field in the same vicinity as a magnetic field. Now if we look at the motion of a charge in a magnetic field, a positive charge added to a magnetic field with a velocity will result in that force on that particle being 90 degrees to both the magnetic field and the velocity, as we discussed. So if the particle is moving this way, it will feel a force this way if it's 90 degrees to the field. That will result in an acceleration in the same direction as the force and force our particle to go in a circle. Now, in the electrical case here, if our velocity is this way and our electrical field is this way, then a force will be introduced which will act on that velocity. But instead of forcing it into a circle, the situation is that it will force our particle to move in an arc. It will accelerate it essentially in the direction of the electric field. So this is much more like gravity. And remember, the force is kq over r squared, as per the Coulomb's law. So you've got two different effects. Magnetic fields tend to force things in circles or helical patterns, whereas electric fields tend to push things into a parabola. So as the magnetic force is always 90 degrees to the direction of motion, the path of your particle is circular. Electric fields can do work on a particle, whereas a magnetic field can't. So the particle's speed in a magnetic field remains constant. Maybe not in the electrical case. So if the velocity of your charged particle is 90 degrees to your uniform magnetic field, the particle will move in a circular orbit. And that magnetic force will give a centripetal force and will give you a centripetal acceleration, as we discussed. So if you go back to your work on mechanics and take a look there, you'd find that the centripetal force is equal to mass times centripetal acceleration. So Fc, essentially, it'd be nice to have a little c here, centripetal force is ma times c here, little c, which is centripetal acceleration. Substituting in the definition of centripetal acceleration was v squared over r. The force is, of course, magnetic. The magnetic force is qvb on a charged particle. So qvb, if we substitute in for F, is equal to mv squared over r, which is our centripetal force. So this simplifies down, and as you can see, what's going to happen here is you're going to end up with r is mv over qb. And this is a specific radius that a particle will move in when it's given a velocity in a specific magnetic field. And this turns out to be a very important result. So this means that things will move in a circle, and you can go back to the circular motion and you can define a few things, such as the period that this object, this charged particle, will move at. So here t now is 2 pi r over v. This is the period, how long it takes a particle to go in a circle. And we can substitute in and say here that r was mv over qb that we just found, and we can result in calculation of t, the period. That'll also give us a frequency of 1 over t, which will be qb over 2 pi m. And this is referred to as the cyclotron frequency. We usually make a little more out of the cyclotron frequency, but given the limitations right now and the time that we do not have, I'm going to sort of leave this alone a little. But just be aware of what this definition is. The thing I really want to get across right now is this. What is the definition of R, and how will that actually influence your particle? So your charged particle enters a uniform magnetic field, and it's going to have a velocity, maybe not 90 degrees to B, and you can look at its velocity. What's going to happen if we throw a particle essentially into a magnetic field is, rather than just move in a perfect circle, if its velocity is not perfectly 90 degrees to the magnetic field, it will continue to move forward, but also in a circle. What do I mean by that? What I mean is you'll end up with a helix as a pattern. Charged particles thrown into a magnetic field at some direction with a velocity of some direction other than 90 degrees will result in a spiral pattern. And we see these things in things like bubble chambers and experiments. So here's a situation where a particle is put into the magnetic field with a velocity, a non-perpendicular velocity, and it's going to end up spiraling. Every time it passed through this sheet of film or bubble chamber, it created a little spark that was imaged, and we essentially got a sine wave. This was actually a particle traveling three-dimensionally through this plane. So the magnetic force is always 90 degrees to the direction of the motion. And that means the path of your particle is circular. But if it continues to move forward, it'll make it spiral in a helix. So essentially this is what's going on. Here's our particle, here's our magnetic field, and always ask yourself when you look at the magnetic field, is this going into the screen or coming out? In this case, this is a circle and a dot. This magnetic field is coming out of the screen. So our velocity of this positive particle is 90 degrees to our field. That means the force is acting inwards. That radius there, remember, is mv over qb. If your particle's velocity makes some angle with the magnetic field, that velocity component along the magnetic field will not change. V will stay essentially the same, but a force will be inflicted on the particle, forcing it to go in this helical pattern. So you can see this helix is at something of an angle here. It's not perfectly 90 degrees to the magnetic field. And of course the force it will feel will be BIL sine theta if we're dealing with a wire. It turns out this is particularly useful because if we are dealing with such things as particle accelerators and colliders, or we just want to trap a particle. This is one of the ideas of creating antimatter to generate electricity, but generate energy for electricity, I should say, and trying to trap it somewhere. You can trap a particle in a non-uniform magnetic field and make it spiral backwards and forwards, essentially containing it in a magnetic bottle. So this is a particularly useful feature. We're going to deal with just with uniform fields. Non-uniform fields tend to get complicated and very calculus-y, if that's a word, very quickly. Now, where can these spiral patterns be useful? Everybody ever play Quake? It's an old game now, but every time you fire what's referred to as the railgun, you end up with this spiral pattern, which is quite accurate. Railguns, it turns out, are actually quite realistic things. You can use a series of solenoids to accelerate a metal particle up to very, very high speeds, essentially replacing gunpowder to propel a projectile. The US military is actually working on this and says that EM weapons, essentially electromagnetic weapons, systems that don't use gunpowder but use electric or magnetic forces, I should say, to propel projectiles will replace conventional artillery that uses gunpowder very, very quickly, probably within the next 10 years on ships. So here's the sort of thing that's going on. Pass a current through this armature here, generate a magnetic field. That magnetic field will in turn then accelerate this projectile with a force F. Give it enough of a potential difference, give it enough current, and you could propel this at very, very high speeds. Where else is this used other than in military capabilities? Such things like the particle collider, the Large Hadron Collider, of course, at CERN, which unfortunately is built into a mountain, making it very difficult to photograph. But as you can see, these large particle colliders, these large particle accelerators, are circular in pattern. Now, there's a reason for that, right? That we want things to go in a helix. We want all of our forces and all of our magnetic fields to line up, and making a circular pattern actually lends itself to that. So you find that all of these large particle accelerators are large circular patterns. Where are you more likely to come across this? Probably in a hospital setting where particle accelerators are used to treat cancers. And anybody who's seen one of these systems, the particle accelerator is usually just in the wall and probably about the size of a table or so. And so usually the patients don't get to see that, but sit in a gantry which can then be moved around to direct the particles where they're needed using magnetic fields. Most cancer therapies use electrons to irradiate the cancers and hit them with high energy and attempt to essentially kill them. That requires a relatively small accelerator. Now, there is such a therapy that's referred to as proton therapy, which is much higher energy and is actually more accurate. But the mass of the proton is much bigger than the mass of the electron, and this massively scales up the hardware that's required. So there are few proton therapy centers in the country or even the world, because here's the patient. Sorry about the state of this particular image, it's the best one I could find, but here is the patient, here is the accelerator, and then you would have to direct the beam through here, direct the protons through here, and then direct them onto the patient. There's a school bus for scale. The accelerator here is enormous. The gantry that you have to put the patient on is huge. So there's the patient sitting here, and there's the protons directed to them. And the reason it's so big compared to a standard electron accelerator is that increased mass for the proton. The Van Allen belts, of course, on the Earth do have a situation where they will pick up particles and channel them. We discussed this in terms of the aurora. But just as a quick aside, there was once an experiment done by the Russian military to fill up the radiation belts to see if they could deny space travel to people. So launching nuclear weapons into the radiation belts and seeing if they could fill them up for a bit. That actually worked. So we've discussed this. We now know that the radius at which our particle can move when it's introduced to a magnetic field is given by mv over qb, essentially a mass to charge ratio here. But what we want to discuss now is really, what happens when we introduce an electric field and a magnetic field. A region like that is referred to as a crossed field. So a force on a charged particle that's going to move in a uniform magnetic field can be balanced by an electric force, and then the magnitudes of your magnetic and electric force can be defined, and you can actually put a particle where you want it to go. So as the electric force is in the direction of the electric field, for a positive particle anyway, the magnetic force is 90 degrees to the magnetic field. So the electric and the magnetic fields in the region have to act on that particle 90 degrees to each other if the forces are balancing. So any region where an electric field is acting 90 degrees to a magnetic field is called a crossed field. That's the simplest way to remember this information. Here we have a magnetic field going into the screen with these crosses. So this is the magnetic field, and then we have what's essentially two capacitor plates. How many times have we seen those? And here's our electric field, 90 degrees to the magnetic field. If we introduce our particle here, our positively charged particle to this system, with a velocity in this direction, it will experience a corresponding force due to the magnetic field of QVB in this direction. It will experience an electrical force in the direction of the electric field, which will be Q times E. Now, by changing Q, by changing E, and by changing B, we could then put our Q wherever we would like to. So essentially, F here will be QE, which is an electrical field term, plus QVB, which is the magnetic field term. So this is the total force acting on a charged particle in a cross-field situation. This is the electrical force, this is the magnetic force. And by tuning these, we can put particles where we would like to. So for a positive Q, the electric force of QE is down, the magnetic force is up. And if we balance our forces, essentially QE will equal QVB. So when the two are in equilibrium and the electric force equals the magnetic force, we can say QE is equal to Q times V times B. Q's on both sides of the equation, so it's going to go away. So V, the velocity of the particle, essentially becomes a balance of the electric field to the magnetic field, or V equals E over B. So any particle, doesn't matter what speed it is, regardless of its mass or charge, will go through that space undeflected. That means particles with greater speed will wind up being deflected in the direction of the magnetic force. Particles with less speed will wind up being deflected in the direction of the electrical force, because the velocity is E over B. And this is useful, because what this gives us is a velocity selector, a speed selector, and that only allows particles with specific speeds to pass through. And it turns out this is extremely useful to us. So Thomson, 1897, not going to go too deeply into this, we do not have time, showed through his E over M experiment that he could deflect rays that he called cathode rays, essentially rays of electrons, by using magnetic and electrical fields. And he made a little dot of light on the end of a screen, onto a screen. So here's what's happened. This is an electron gun, essentially an anode. It's firing electrons into here, it's in a magnetic field, and is using his electrodes to deflect the ray and put them where he wants to. Here's a negative and positive plate in a vacuum tube. He could then see a dot of light and figure out how much he could move this electron. And he essentially said that electrons are deflected by electric and magnetic fields. And this was in 1897. And it turned out that you could make this speed selector. This turned out to be pretty useful because this is the dawn of television and making little dots of light on a screen due to a cathode ray tube, or essentially an electron gun. And this is the way TVs used to look, right? This is an old monitor and the inside of it. And, if you go and look at old sci-fis, they kind of got that wrong. Here's a picture from Alien where they still had old CRTs, and here's a lot of old TVs and monitors that used this technology. So Thomson's experiment was really just varying E and B. Now, a really good example that people might want to think about the original game Pong from the 1970s, where you had two paddles that just moved up and down on the screen and a little dot of light that went from the left to the right and back again. Now, to move that dot of light, all the computer was really doing was telling a monitor to change either the electric field or the magnetic field, which would move the dot of light to the left or to the right. So in terms of CRT technology, we've kind of left this behind, right? We've all got flat panel monitors now, or little laptops with just a flat screen in them, and loads of CRT glasses stuck out there, stockpiled in warehouses, and basically it's being destroyed and gotten rid of. But the principle is still useful to us. And the reason the principle is useful is because we can create things like the mass spectrometer, which some of you might encounter, and that's what I really want to get into here. And we've had mass spectrometers since about 1919, and what we can really do is determine the presence or the abundance of isotopes in a sample that we give to a spectrometer. So essentially, very similar system. Here we have a big magnet, and then we have essentially a electrical field, and then we can accelerate our particles through this system, and then we'll, through our velocity selector, remember the velocity selector will actually be sort of mass sensitive here, and we'll end up with different particles taking different paths from the lightest to the heaviest, and this will separate out different isotopes or different elements in a sample and give us a counter at the end in a detector and tell us what those particulates actually are. So in a mass spectrometer, ions are accelerated by an electric field and then enter a uniform magnetic field. If the ions start from rest and then move through some potential drop of delta V, then the kinetic energy when they enter the magnetic field equals the loss in the potential energy. So in other words, half mv squared equals q delta V. V here, this is potential difference. This is a voltage, not a velocity. This is the velocity in the kinetic energy term. So two V's here meaning different things. That's why I put delta V here to say it was a potential difference. So this is velocity, this is voltage. So in terms of the mass spectrometer, the ions will wind up moving in a semicircle of some radius, which will be mv over qb. They'll strike some sensor, and then you can figure out what the mass of that particular object was. So essentially you'll have an m over q ratio. So let's take a look at one of these problems rather than me throwing more definitions at you. I really want you to focus on the problems in this section. There's a lot of definitions and a lot of material that covers a lot of background, but I think that particle accelerators and especially things like mass spectrometers are things you might encounter. So an electron here is moving 90 degrees to a magnetic field and following a circular path. The magnetic field is 4.3 times 10 to the negative 3 Tesla, and the R is 3.7 millimeters. What is the speed of the electron? This is a typical kind of question. We've got the mass, we've got the charge here given because it's basically an electron. So we've got a mass of 9.11 times 10 to the minus 31 kilograms and Q of 1.6 times 10 to the minus 19 coulombs, where R is mv over qb. What's the speed of the electron? Well, V is rqb over m. Substitute in 3.7 times 10 to the minus 3, 1.6 times 10 to the minus 19, 4.3 times 10 to the minus 3 over 9.1 times 10 to the negative 31 gives us 2.8 times 10 to the 6 meters per second, or about 1% of the speed of light. So I've given you a lot of background there, and I really want you to sort of hit on the things that I've discussed in terms of examples. So let's get a bit back to talking about the mass spectrometer situation and the motion of our charged particles in a magnetic field. So in a mass spectrometer, ions of different mass and charge will move in circles of different radii. And that's useful because we can separate different isotopes of the same element. So here's our magnetic field, and this basically coming out of the page. Here's our sample being injected at some velocity. Here we're dealing with uranium, and there's different isotopes of uranium. And what will happen is those different masses, uranium-235 or uranium-238, will move in circles of different radii when they're injected into the field. So that will cause uranium-235 to take this arc, uranium-238 to take this arc. Now, when you look at the news, and obviously the news is full of only one thing these days, but we used to discuss things like nations like Iran making nuclear weapons and things like that, and people be objecting to it and saying that they were using centrifuges to enrich uranium. Those centrifuges were not essentially a mechanical centrifuge where you stuffed uranium in and spun it round. They were these type of centrifuges where you could put in a sample of uranium and you could get out the high mass stuff, you could get out the high energy weapons grade stuff and throw the rest away. So let's take a look at this from the perspective of a mass spectrometer rather than weapons of mass destruction. So here we have nickel 58 ion, and basically it has a mass of 9.62 times 10 to the negative 26, and we're going to accelerate it through a potential difference of 3000 volts, that's 3 kilovolts, and put it into a magnetic field of 0.12 Tesla. That's a fairly hefty magnetic field based on what we've said before. We want to find out the radius of curvature of the ion, and we want to find the difference in the radius of curvature from nickel 58 to nickel 60. Those should be superscripted. So, find the radius of curvature. This sounds like a complicated problem, but it really isn't. So, half mv squared is equal to qv. That was a statement we made. They're going to move in a semicircle. The radius of that will be r equals mv over qb. Now, v, essentially v squared, is r squared, q squared, b squared over m squared. We're substituting in here. Substituting for v squared in half mv squared equals qv. So, m over q becomes b squared r squared over 2 delta v. So, r essentially becomes 2m delta v over qb squared, giving us 0.5 meters. So, the radius of curvature of a nickel 58 ion is 0.5 meters. Don't worry, if this appears on an exam, it would only be in a bonus sense. So now we want to find the difference in the radius of curvature between the 58 and the 60. So let's find the ratio of R2 to R1. Essentially cancel this out. We'll end up with M2 over M1. That means R2 over R1 equals M2 over M1 rooted, which is a root of 60 over 58. This is just an example I want to show you as to how this works. That means that R2 now is essentially going to be this, 0.5. R2 minus R1 is 0.5 minus 0.501. That'll give us 0.003 meters, or 3 millimeters. So these two different ions will come out of a mass spectrometer 3 millimeters apart. Your detector will count them, and you'll be able to identify which ions of nickel you have at those positions. Now, I didn't want to scare anyone with this stuff, and I just kind of mentioned it, and given the pace that we're running at, I want you to get the idea here as to how these things work. This is not a calculation I would expect you to reproduce in an exam situation. I do want you to know R equals mv over qb, however, and that half mv squared equals q delta v. This is an application of it that you may see working in chemical or biological fields, and I wanted you to know how this worked. But those are the two equations you should focus on. So finally, again, I've truncated many things. The cyclotron is essentially a device which works on this principle and can use high energy particles to bombard atomic nuclei and cause nuclear reactions. And these have been around now since the 30s, and they essentially use two gigantic magnets to put particles into circular paths and accelerate them. So you're using crossed fields, magnetic and electric fields, to eject particles of the right velocity. And as I said, This is the kind of thing you might find in a cancer treatment facility. This is the machine which actually directs the particles, but behind this there would be a particle accelerator which would accelerate the electrons, and then this would then focus them onto the patient. The cyclotron's also located on the bottom of a Ghostbusters backpack. Okay. Finishing up applications of magnetic fields, other places you might see magnetic fields might be sunspots on the sun. These are caused by looping magnetic fields. Here's a constant, unbroken loop of magnetic field on the sun. And these loops essentially are made of bright gas, are made of magnetic fields, and will actually make loops of bright gas come up and essentially erupt on the surface of the sun. So that's the end of our discussion on the applications of magnetic fields.